Designing table-valued and scalar functions. So we have a design nugget here. This one is all about how to properly design your data access layer. How front ends are going to interface with the underlying schemas using our middle layer, which is going to be views, stored procedures, and functions. So we're going to kick this nugget off with just a brief discussion on what data access design is all about, what code non-regression is, and how we can avoid breaking front ends when things change in the back end. And then we'll just briefly go over the different types of functions that are out there and a little bit on row-based versus set-based processing. And then we will jump into the virtual nugget lab. We'll take a demo on table-valued functions, both inline and multi-statement table-valued functions. We'll take a demo on scalar functions, how to create them and work with them. And at the end, we'll take a demo on code non-regression. We have a front end that we used in a previous nugget, and we will see how to properly change the back end, possibly change our middle layers so we do not affect the front ends. Let's do it. So the main concept for this objective is ensuring code non-regression, which is essentially ensuring that anything that touches our schemas isn't going to break if we change them. And how we can circumvent this from the design perspective is to ensure that all of our data calls don't hit our table schemas directly. Applications shouldn't do this. They shouldn't go right against our table schemas. What they should do is access a data access layer, a DAL as we call that, and they're going to do that using views, procedures, and functions that we create on the database side. So by doing that and creating that data access layer, we break the schema dependency and we create what are known as interfaces to those underlying objects. So the whole idea there is to shield our front ends from back end changes. And since we're in control of our data access layer and our schema, if we do need to make schema changes, we can update the implementations inside of our data access layer, not the signatures. Signatures are how front ends interface with our data access layer. A signature to a stored procedure, for instance, is the parameters. The name of the stored procedures and the parameters. That's all the information that the front end needs to call our stored procedure. And just another side note here, this is where optional parameters are totally awesome. Because if you do need to add parameters, you can add them as optional parameters. We still won't break the front end, but that functionality will be available so when they get time to get around to adding it into their existing applications, they can do so. But that's the idea. We don't want to break things that hit our database. And we do that by implementing a data access layer, an interface that front ends tap into and that accesses the underlying schemas. Again, we want to avoid any sort of application or anything accessing our underlying data structures directly, because that will cause problems when it comes time to change those underlying schemas. So that's the skinny on code non-regression, and we'll get an example of it when we get into the virtual nugget lab. Now, row-based versus set-based operations, we have a full-blown nugget dedicated to this in 70-461, but I do just want to go over it to talk about it a little bit. Row-based is procedural programming. It's a way of thinking about coding it from top to bottom, line by line. And if you're a developer and you're new to Transact SQL, then you've been stuck in that mindset for a while. And when you come up to problems, and I know because I was the same way when I was a developer coming into SQL, every time I thought of doing a query, I'm like, my mind just went, okay, row by row. I'm gonna create a loop because loops are awesome and they're the answer to everything. So I'm gonna create a loop and walk through this row by row. And when I'm on this row, I'm gonna go run a query against another table to look at that row. And that is just not the way to do it in the world of SQL. Set-based operations are the way to go, and it's because it acts on the entire result set. So you can really do a comparison between procedural and declarative. Procedural is thinking about it from top to bottom. Declarative is thinking about it with the end in mind. So in the world of SQL, when we write a query, we're really going backwards. We know what we want. We know the answer ahead of time. It's like playing Jeopardy. You know the answer, you got to find the question. That's pretty much what it is with SQL. We know the answer. We know how we want our results to be. How we get there is by working from the results backwards by writing a SQL statement. So that's the big difference. And another way to think about that is row-based processing. You're in the row mindset, row by row. Set-based processing, you're in the column-based mindset. You're thinking about affecting entire columns rather than rows. So just another way to think about it. So row-based, while they're easy to write, especially if you are coming from the world of development and you're used to writing code line by line and watching it execute line by line. So it's easier to write generally because of the mentality, but it's terrible on performance. Cursors and loops are just the worst thing you can do for performance inside of your SQL queries. So generally you want to stay away from, unless you're doing like administrative things, file I/O, streaming, looping through databases to do backups, administrative stuff. It's okay to do cursors and loops, but for data stuff, stick with set-based operations. They may be a little more difficult to write because, again, you're writing it from the inside out, but it's as good as it gets when it comes to performance. Let's switch gears here and work with functions. So functions are a lot like stored procedures. They're just a named set of code that sits on the server. They can accept parameters and return results. The big difference, though, is that we can use functions from within queries to work on data within those queries. We've got a bunch of different kinds of functions. We've got built-in functions that span many categories: mathematical, string conversion. We've used many of them. System functions for working with SQL Server specific stuff. Scalar functions for returning a single value. And we've got table-valued functions for returning a table. And there are two flavors of table-valued functions. One called inline, which just basically means we're going to return a table. There's also multi-statement table-valued functions, which allow us to create a table on the declaration of the function, insert data into it, and then return it. So we'll look at both of those in the virtual Nugget Lab. With that, why don't we head into the virtual Nugget Lab? We'll start here by working with table-valued functions. We'll move into scalar-valued functions, and then we'll look at how to ensure code non-regression. All right, here we are in the good old virtual Nugget Lab. Let's bring up SQL Server Management Studio. We have a new project inside of our solution called 11.design UDFs. And let's start here with table-valued functions. So inline TVFs are pretty straightforward. Again, we're just returning a table. We're not specifying the definition of the table. That is going to get inferred from the query inside of the function. So it's literally create function, name of the function, followed by any parameters. You can still use parameters here. Returns table as, and then we're returning the results of a query. Pretty straightforward here. So let's create this one. And then we can also see it here. Let's go into Nugget Demo DB. Let's go into programmability, functions, and there is the table value function we just created. And by the way, if you right click on here, you can actually see SSMS will prompt you which table value function you want to create. If you create inline, you can see that the structure of it is just what we saw here. Create function followed by the name, followed by any input parameters, and then returns table. This is going to be different from a multi-statement table-valued function, because if we look at the definition here that they give us to create one, the template, then you can see that we still have input parameters, all that's the same, but returns can be a table variable, or we can define the table definition on the fly. So that's going to be the big difference here between those two. So now we can treat a table-valued function just like it was a table. We can do a select from it, or like it was a view, whatever we wanted to here. And this one will just go and find all the current upcoming courses that are not marked as completed. So there it is. There it is. That is a table-valued function. Again, returns a table, but that specifically was an inline table-valued function because it just inferred the table from the query results. Let's look at a multi-statement table-valued function. So you can see right off the bat that we are defining our table structure within the definition of our function. We're also accepting an input parameter for this one. We're going to get courses broken out by category and year based on a start year, and it'll go all the way up to the current year that the user passes in. And this is a horribly inefficient function because I'm using a cursor in here. And I wanted to make this as ugly as possible just so you could see, if we converted this to a set base, it'll just look much cleaner and easier to work with. So what we're doing here is we're going to create a cursor that goes from that start year to the current year and generates all the years. In fact, here, let me just show you this, what it looks like. If we just highlight the CTE here and execute it, this is just going to generate a list of years. And that's what the cursor is going to use as a base to loop through. So it's going to loop through once for each year, and then it's going to use that year to get a count of courses, and then also to get the categories broken out by course. And it's going to stuff all of that then into this table. And at the end, we just destroy the cursor, and then will return that table to the caller. So let's create this big honkin' function here. All right, good to go. We created it, and now let's execute it. So you can see we're going to call it just like we would call any table-valued function, treat it like a table or a view here. Select star from it, only we're going to pass the input parameter and order the column by category and then by year descending. So if you execute this, here's the results. all the nugget counts, the course counts, broken out by category, broken out by year. Now let's fix this because, see, cursors are hard to read. There's just so much supporting code around it that it's difficult to read. And we don't need pretty much all of this. We can get rid of all this ugly code here. All we simply need to do is have this one query right here that is pretty much going to do the same exact thing. The only thing we'll need to change here is the completion date greater than or equal to the start year. That should do it. Let's make sure we got everything here. We've got the year going in, we've got the category going in, and we've got the count of courses going in. So this should give us the same results without the ugly loop. So it's just one set-based operation now. And should we get the same results? We do. And believe me, the execution plan for that was way better than a cursor. A cursor is going to create a plan for every time it loops, and it's going to be pretty bad on performance. So this is certainly the way to go. Set-based operations, and there you go. There's table-valued functions. Let's move on to scalar functions. So scalar functions just return a single value. And we actually created two scalar functions for computed columns inside of our course table. If you remember here, in our course table, we have total nuggets and total durations. These are just simply computed columns that run on these functions. So the structure's very similar to table-valued functions. The big difference here is that we're returning a single value. So we specify the data type that we're returning, and then whatever we do in the body of our function, the last thing we're going to do is return a value or a variable of that type. So we already have these two functions created. Let me just show you here. If we head down to scalar valued functions, there they are, get course duration and get course nuggets. And we can see on our table, if we just head into our course table here, we can see the definition says computed. And let me just copy this to the clipboard here. Let me right click, script it as a create to clipboard, and let me just paste it right up here. And you can see here's our definition. The definition of these columns are the table or the scalar functions, and we pass as the parameter into them the course ID associated with this table. So that way the course ID will get passed into these, and the results will then get piped out as a computed column. So that's that. And we can also use these, by the way, outside of, we don't have to use them as computed columns. We can use them in queries if we want, like I have here. Here I have a query that uses the scalar UDF on both of them, just a query that goes against the course table and then calls both of those functions, pass in the course ID of our query, and we will get the same results here. And there it is. And then for reference down here, I just call the table directly and these columns directly, which are built on top of our scalar function anyway, so we'll get the same results. So those are some good examples of scalar valued functions that return a single value. Other good examples are just generic functions that just work on data, like a date format, for instance. That's a popular thing to do. Or I've created functions many times that strip time off of a date. For a report, you just want the date, you want to strip the time off. That's a great example of a very generic user-defined function that you could put in the master database and use across all your databases. So lots of good uses out there for scalar UDFs. Now the last thing I want to go through here is the big objective, and that is ensuring code non-regression. So the problem once again is that changing schemas affects applications and even our data access layer. Anything that touches our schemas will be affected if we make a change to them. So the solution then is to create a data access layer to interface with the schema and ensure that all access outside of our database flows through our data access layer. Now, we have down here, we have the full picture. We have an application that we built in our stored procedures nugget. We have a data access layer through that stored procedure that we built in that stored procedure nugget, and we have a schema to work with. So we're going to test this out. And first, I just want to say that we properly designed this along the way, because if we were to do something crazy, and by crazy I mean alter our table, our trainer table, and let's say we were feeling evil that day, and we decided to put a new column right smack in the middle of the table. Who does that? Hopefully nobody. But by doing this, we could be causing all kinds of chaos, because especially for those stored procedures that do, or views or anything that do a select star, and then applications that access these fields ordinally rather than by name, we're just asking for all kinds of trouble here. So let's do that. Let's add this column right in the middle. All right, so we've got a higher date column in there. We could have also added at the end, which would have been a better way to do it because less chance of breaking applications. You should always add columns to the end. But here's the result. So right now, we should still be good. In fact, if we go into our Nugget Lab files here for 10, stored procedures, go into CLR projects, go into our trainer profile. I'm just going to open up the bin directory directly and open up this application. If we bring this up and start clicking around, look at that, it still works. Nothing broke. It's working. Excellent. So that's good. That's because we properly designed it. Even if they were to add columns all over that table, we're good to go because we're protected by our middle layer here, which is our stored procedure, our data access layer. Now, let's say that when we built this stored procedure, we weren't thinking straight that day, or whatever the case may be. And let's just comment it out here. And we did a select star. All right, let's do this. Something like so. Select everything. All right, let's modify the stored procedure now. And now let's go around. Yeah, see? Yeah, that's going to cause problems. We've got errors no matter what we do. We can't do anything in the application because we changed our interface. We changed the middle layer. So now applications that communicate with our data access layer are going to have problems because it's not what they expect. We changed the output. So by keeping things consistent and keeping it all in our data access layer, we can really prevent our front ends from blowing up. Like so, right? That's better. So the two biggest things to take away from this is one, design a data access layer and funnel all outside traffic through it, so that will protect us from schema changes. And number two, design your data access layer accordingly so it's protected from schema changes. Oh, and you know what? There is the third part to that. The third part to that, and this is really cool. If, say, you wanted to release version 2 of this stored procedure, so you needed to change the signature. Remember, your signature is this right here, how our applications interface it. They do that using the name and the parameter set in the stored procedures case. But let's say that we did want to release version 2. We needed to add a new parameter to this. We'll call this new param int. Just make sure you make it optional. Nullify it, because this will not break our existing apps. And just to prove that here, let's create that. Let's go back, open up our app. Does it still work? It does. See that? Very cool. So that's that. That's how we can properly design our data access layers to ensure code non-regression. In the CBT Nugget, we learned how to design table-valued and scalar functions. We started off with data access design, where we went over all the objectives. Specifically, we covered what code non-regression is and the difference between row and set-based operations. We jumped into the virtual Nugget Lab, where we learned all about table-valued functions, saw the difference between inline and multi-statement table-valued functions and how to build each one of them. We took a look there at scalar functions and saw how to use them, and also how to use them as the engine to a computed column. And then at the end, we took a demo on code non-regression and see how to protect our front end by shielding the back-end schema with a middle data access layer. I hope this has been informative for you, and I'd like to thank you for viewing.